representation from Theorem 1 to 6 of solid geometry. I am Angeli Padilla and I am Lira Monterola at your service. Theorem 1. Two intersecting planes meet in a straight line.
The intersection of two geometric figures is the set of all points common to them both. Now, let me ask you a question. Is these two figures here are both solid? Yes or no? The answer is yes. Yes, because in three-dimensional figure definition, not all of its parts lie in the same plane. In this solid, it has 6 figures. This one, this one, this one, this one, this one, and this one. Therefore, it has 6 planes. This one, it is also a solid because it has also a 6 face. This one, this one, this one, this one, and this one. In Theorem 1, it states there that two intersecting planes meet in a straight line. For example, this plane here and plane here intersect in a line. And also, in this solid, this plane here intersect in a straight line. According to action 3, two distinct planes cannot meet in one point only. Therefore, we need at least 2 points. And those 2 points pertain in a straight line. Therefore, the intersection of two planes is a straight line. And that proves our Theorem 1. Theorem 2. A plane is determined by a line and a point not on it, two intersecting lines and two parallel lines. Let me ask you, how many points determine a line? We have at least 2 points that determine our line. For example, this is our line here, and a point not on it. To prove that this line and point determines a plane, we have axiom 2. Axiom 2 states that through 3 non-collinear points, one and only one plane can be passed. Therefore, our line has 2 points and a point not on it. Therefore, we determine these 3 non-collinear points. And these 3 non-collinear points, according to axiom 2, we have a plane. Another one, two intersecting straight lines determine a plane. How is this possible? This line here intersect, right? And this line has 3 points, which are non-collinear. Therefore, in axiom 2, to 3 non-collinear points, one and only one plane can be passed. Another one, we have 2 parallel lines determine a plane. This line here and line here determines a plane. Why? Because we have this line, and in this line we have a point, 2 points. Either here, infinitely many points in a line. Therefore, in axiom 2 to 3 non-collinear points, one and only one plane can be passed. Therefore, in our Theorem 2, we then prove that by line and a point not on it, 2 intersecting lines and 2 parallel lines can determine a plane.
Theorem 3. If a line is perpendicular to each of these 2 lines at their point of intersection, it is perpendicular to the plane of these lines. Now, in our previous discussion, we know that 2 intersecting lines determine a plane. And let's say that their point of intersection is line P. Now, if we draw a straight line to that, which is perpendicular line to these two intersections, then we can now say that the whole plane is perpendicular to this line. Now, example, let M, this our plane, be the plane of line 1 and line 2. Let line 3 be any line in M through P. So this is our line 3, line 1, line 2. This is our line 3. It passes through point P. Draw a line meeting line 1 and line 2. So we can draw a line here or there, line 1 and line 2. And E and F be points on the opposite side. We have a point here and another point there. So we know that any intersecting lines meeting through P will be perpendicular to our line 3. And also, two intersecting lines determine a plane. So we can now prove or we can now conclude that this line 3 is perpendicular to our plane M. Theorem 4. Through a point, there is one and only one plane perpendicular to a line. Suppose this is our point P, which lies on our plane M. Now, given a line L, we put this line, so we can say that this line is perpendicular to our point P. Then, if you will draw another line which goes through point P also, and another line, and you can put infinitely many lines, we can always say that these lines is also perpendicular to our line 1. Now, to prove that only one plane can be perpendicular to a line, only one, not another plane, because if we put it here, this is not perpendicular to our line. What will happen is this will be parallel. Put it there. This plane here will be in our plane M. So only one plane can be parallel to our line 3. Again, we now go to our theorem number 29, which states that one and only one perpendicular can be drawn to a line through a point, whether that point is on the line or not. So, this point will only have one line which will be perpendicular to this plane.
Amen.
Through a point, there is one and only one line perpendicular to a plane. Suppose we have this plane M, and this plane M contains point P, and this point P is in our plane, and then we have this line 1 and line 2. Suppose M is our plane and point P is our point in the plane. This is line 1 and this is line 2. The intersection between these two intersecting lines is point P. And we have another plane, and this plane is plane N, for instance. This plane N is perpendicular to line 1 at point P and meeting this plane M in line 2. Therefore, this point P here and this point A here is a line in N and perpendicular to our line 2. Then PA is also perpendicular to our line 2. So, this would be proved by Theorem 3. This Theorem 3 states that if a line is perpendicular to each of two lines at their point of intersection, it is perpendicular to the plane of these lines. And that is our theorem number 5.
oblique lines from a point to a plane meeting at equal distances, the foot of the perpendicular are equal. Conversely, two oblique lines from a point to a plane meets at equal distances from the foot of the perpendicular are equal. Okay, suppose we have these three lines. We have one perpendicular line which is also perpendicular to our solid and our plane. We can see that these two oblique lines, anyway, what is an oblique line? Oblique line is the exact opposite of perpendicular. If your lines are not perpendicular and they are not parallel, then your lines are said to be oblique. See this? These two lines here are not perpendicular to your plane, and they are also not parallel to each other. That's why they are called oblique lines. Okay, back to proving our theorem. Suppose that according to our theorem 6, these 2 points in our line is equal in distance to the foot of our perpendicular. What is the foot of our perpendicular anyway? Now, in our previous discussions, the foot of our perpendicular is the point of intersection of your plane and your line. Given that from this point to the foot of our perpendicular, let's have this point A and point B and point C. AB is congruent to CB. Now, through reflexive property, our perpendicular line here is a common side on our triangle. Suppose we have two triangles here and we have a common side on the middle. Let's have this point P and point B. So PB is our common side. Now, through reflexive property, PB is equal to PB and AB is equal to CB. Now, through SAS postulate or theorem 26, this included angle here, now we know that if a line is perpendicular to a plane, their angle equals to how much? 90 degrees, that's right. Now, according to theorem 25, two triangles are equal if two sides, one side here, another side there, are equal and an included angle. We have our included angle, the perpendicular angle, which is 90 degrees. Of one triangle is equal respectively to the two sides and included angle of the other. Now, with axiom 23, congruent parts of equal figures are equal. Therefore, we have now, through this example, we will have a proof that oblique lines from a point to a plane that meets the plane at equal distances through the foot of the perpendicular are equal.